This is the Research Computing with Python course. Welcome. We're having the first lecture here. It's a little tight and a little warm. Starting next Thursday, we'll be in a bigger, different room. So don't get discouraged because of that. My name is Ramses van Zon. I'm one of the analysts at Scinet. And so I and Mike Nolta, who's not here right now, will be giving this particular course. And today we'll go over sort of the details of the course. What is it about? Topics, how is it structured, what to do with homework, etc. And then towards the end, we'll also get in a little bit into Python, the language that we'll be using for this course, just to get everybody up to speed. Just to get an idea of my audience, who here has some experience with Python already? R, C, or Fortran? Okay, so most people have something, right? This is a good start, because that's the idea. You have to have a little bit of program experience, because we're only doing this in 1 month. If this was spread out more, I'd say, well, you could learn on your own while you're taking the course. You have to understand a little bit about programming, because we want to get to the research computing part. How do you use Python to do what we call research computing? So this is sort of a mini graduate style course. So graduate courses tend to have lectures and span at least the semesters. This is a month, 4 weeks, 2 lectures per week, each an hour. They'll be from 11 to 12 on Tuesdays and Thursdays. And there's a reason why they have this format particularly. It's because by doing so, they also count as mini courses for astrophysics and physics and chemistry students. So if you're from that background, who's here, physics, astrophysics, or chemistry? A couple. You could take this as one of your modular or mini courses. If you're not from that background, which is the majority of you, ask your graduate office how on earth you can make these things for credit, because we would like to give it for credit. We just can't, because it's not recognized as such. So this is why it's in this style, and that's why we also do things like assessments or assignments, which we grade, and the assignments will be the basis of the grades. But by and large, the assignments are there for you to practice what we show you, and for us to give feedback on your progress. So even if you're not taking it for credit, I would really suggest doing the assignments, and that's the way to learn how to program is by doing it. We've set aside some office hours on Wednesdays between 2 and 3. You can email or ask questions on the website forum in between. You don't have to come, but we'll be making sure that somebody's here if you come by to answer questions during that. Lecture dates. So that's sort of the how. This is the what. So these are the topics that we're going to look at. We're going to look at Python programming. Python is a scripting language, as I'm sure you've Googled if you didn't know it before. It's a scripting language that means that the Python interpreter takes one line of Python code and does it. You type in a new one, it does what you tell it, which is good. It's very flexible in that sense. So we'll talk about how to program in Python, how to use that to automate things you might have. We'll use version control. So one of the things we want to really instill here is that when people start programming, they're already happy when they get a script that works, which is great. But then a month later, that script makes no sense to them anymore. Or they start working on that script, they change a little bit, and it doesn't work at all. It's combined both the two, a month later, and a script that no longer works, and you might as well not have ever written a script. So we're going to teach you ways to approach programming. Just a few simple things that if you use those, will make it easier for you to go back to a previous version, to know what was done, to basically best practices as we are learning this. And it's better to do that as you're learning it on sort of pet projects and assignments than when you don't find you have time for it in your actual research project. So one of the things we're going to teach you is version control, modular programming, and then we'll talk a little bit about visualization. Python has a package that does that very nicely. And then we'll take a few select numerical methods to sort of illustrate what you could do with Python. These methods are slightly tailored towards the physical sciences. We might change that if that's something you would like, but by and large, this is an introduction to research computing with an emphasis on the computing part. Okay? So If you have data that is in a large array format, the things that we'll be talking about will apply. Unstructured data, we're not touching that much upon. So it's really more towards numerical. That's sort of an entry to programming as well in physical sciences. Okay, and that's kind of the background on what we're doing. A lot of it, even if you're not in physical sciences, will translate. It's just towards the end, a few of the use cases might be somewhat unfamiliar, but as I said, we can see how it goes by then. So as I said, we require you to have a little bit of programming experience. Otherwise, the learning curve will be too steep and you'll just basically quit. And we don't want that. Software that you'll need. So we're going to use Python. Now, for the purpose of this course, we'll ask you to install Nthought Canopy, which is one particular package of Python that comes with certain packages already pre-installed. Python is very modular, so you can have a bare bones Python with which you can do nothing but print things, essentially. But then there's useful packages like NumPy, SciPy, Matplotlib that we'll all go into that we'll be using. And rather than installing each of them separately and figuring out how to do it on a Mac, on Windows, on Linux, by taking a sort of a prepackaged form like Nthought Canopy, we all have the same environment. We all have those packages available. And we don't have to worry about installation stuff. And again, this is very important if our course is only going to be a month. We don't have a month to get your laptop set up properly. It's free. If you register with your @utoronto.ca email, you can get the academic license and you get extra packages. So I would try that if I were you. And that's the environment we'll be using. If you already have a Python, I'm not going to forbid you to use it, right? But you might have some, like, it's possible you have trouble, and then you could always install Nthought Canopy besides a Python you already have. So there's no, you can have it not be your default one and just work in that if you want. Okay. So that's what we're going to do in terms of software. There's links to Nthought Canopy on the website, so you could start. The instructors, as I said, is myself and Mike. Grading will grade the homework. So every week you'll have a homework assignment. It's due the next week, and we'll grade it. I have a sign-up sheet just to get an idea of who's here. As I said, attendance won't be mandatory because we'll see from the assignments who is serious about it. But I don't have a pen here. Just put a check mark next to your name. We don't need signatures. We'll trust you. It's really because it's not part of the grade. It's just for us to get an idea who's here. That clear? Who here was in the R course, by the way? A good few. So it's set up similarly. We have our course website. That's going to be sort of the central point of a lot of things. You log in with a sign-up account or a temporary account if you still have that. And then go to Intro to Research Computing. So it's over here. And then on that, looks slightly different. This is an old picture, but there'll be things like the syllabus. There'll be an assignment Dropbox where you put in your assignments. There'll be lectures. There's nothing here yet, but they'll be under file storage. So the PDFs of the lectures will be there. Recordings will be put there. So in the content navigation on the right, you'll have a list of recordings. So we'll try and record everything. We broadcast our lectures as well through Google Hangout on Air, just because we found that quite a few people would like to take the course, but they can't be here in person. So if you can't be here one day, that's fine. You can either watch the recording or see it live online. There's a chat too that sort of is active during the lectures. It's active right now. So as I said, there's some links to the Canopy installer, and there'll also be file storage, PDFs, assignment, chat. There's a forum. This can be very useful. You can ask questions. If we don't answer them, one of the other students might have an idea. So you can, so this can be useful for asking questions while you're doing or while you're playing with the material. Don't forget that little content box. That's where the syllabus is, and the calendar posts. Okay, so that's about the course and kind of what we're going to do. Any questions so far? Good. Research computing with Python. There's two things here, or three. Research, I'm going to assume you know what research is. And Python, which is this programming language that we'll use. And then research computing. And that's not particularly well defined, so I'll just give you a few ideas of what we mean with this, and they'll give you an idea of what we are trying to teach you here. So this could be called research computing. It could be called computational science, scientific computing. Depending on what you do exactly, it could be called data science. It could be called a lot of things. But in essence, it's whenever you're using a computing device, a computer, to figure out something about your data or something about the world or a model. So you could be processing data mining, processing. You could have a model that's too complex to solve analytically, and you sort of simulate it and see what happens rather than doing this on paper. You might have some experimental results you have to interpret using a theoretical model. You might want to simplify a model you have with a simpler model, do some fitting. You might want to visualize data that you found. Those are all parts of research computing. And most of these parts are not taught to you. You're just supposed to know what to do with these. You get taught the theory of your particular subject matter. You might be taught something about the instruments that you use to measure things. You might be taught some math to solve models. This part is presumed to be self-explanatory, and of course it isn't. So good for you for being here, because we'll try and make that step towards having a productive research computing life a little easier. So I don't particularly like this slide too much, but people call computation the third leg of science, the first two being experiment and theory. That distinction between experimentalists and theorists has been around for a little while. The idea that computation is a third way of approaching science is true, but it borrows a little bit from both. It's definitely got a lot of theory in it. You compute something, you make a model, and that's all on the theory side. And it has experiment too, especially if you're processing data. That data comes from experiment. It's even worse. If you're solving a model on a computer, that's like doing an experiment. You do not know what's coming out. It's not just math. There's approximations in it. There's experimental methods that help do this well. So in essence, that computation can learn both from theory and from experimental best practices. Now, we're going to focus on the things that are sort of unique to that. So if you're an experimentalist, we're not going to teach you doing experiment. If you're a theorist, we're not going to teach you how to solve an equation. The things that are specific to computation is what we're going to do. So I'm assuming most of you are here because you're either interested in Python and research computing, or your research is taking you to a point where you can't just point and click in your favorite visualization program or data analysis program and get your results. You have a little bit more complex stuff to do. And if you're at the cutting edge of any sort of research, that is not uncommon. So programming is often needed. Could be scripting, could be making a workflow of existing packages work. That is still programming. That is still something you would have to tell the computer exactly what you want to do. And that's the difficult part. And one of the things that we're going to attack here. You have to tell this computer what to do, and the computer, if it's not already programmed in, if it doesn't fit within that application visualization package, is extremely stupid. Computers do not know anything. They know bits, and even that. So we have to be quite detailed in in what we tell to the computers so it can do what we want it to do. You can't just say, well, just analyze my data and see if there's a trend. That is not a command that the computer understands. We have to be way more detailed. Now, people have been programming computers for a while, and so some things are programmed in, are ready for you to use as building blocks. So you don't have to go to the lowest level necessarily. You can use building blocks. And depending on how deep you go or how unusual your needs are, you use different tools. So more high-level languages like Python have a lot of built-in functionalities. If you want to look up something in a table, Python has that lookup function already. You don't have to implement that. But that's because you're using Python, and it is sort of a high-level language. If you're using low-level languages like Fortran and C, you might have to be way more explicit in what to do. You might have to step through an array of these things and check each of them, whether or not it's the value you're looking for, if you were looking for something. So the detail that you have to go into depends on the language. Now you might wonder, why are we not all programming Python? Why is anybody still doing that low-level stuff? And that's because they are probably performance bound. They have probably got a problem that if they did it in Python would take 100 years, and if they program it well in C, it might be doable in a year or less, just because they can do optimizations at that lower level. I'm not saying this is always the case, but a factor of 10 or 40 is not uncommon if you go from pure Python to, say, pure C, if you know what you're doing. But now you have to know what you're doing in C. So if you're interested in that kind of low-level performance stuff, come to our next mini course. It starts in the winter. We actually have 3 of them: software development, numerical tools, and high-performance computing, going all the way from January into April, if you want that kind of stuff. And it's interesting, and a lot of us do this. But if you're new to programming, you just want to know how to automate your workflow, you're in the right spot right now. So we're on this level, which you call an interpreter, where we have these building blocks. One line at a time is interpreted by Python, and it's executed. Because it's one line at a time, it can't do certain optimizations. It can't say, oh, I see a shortcut in what you're doing, because it sees one line at a time. These low-level languages like C and Fortran, they are compiled languages. The compiler takes your whole file, all of the commands you want to do, and sees if it can reshuffle them, if it can omit certain things because you're not really using them. It can do things more cleverly, as long as the end result is the same. So it can do. That's one of the reasons you can do things faster than an interpreter. So it's good to know the difference. An interpreter tends to be slower, not line by line necessarily, but definitely in a whole program. A compiler is faster. Python is an interpreted language. So we're going to be on that level. We're going to be able to do a lot of things in Python. It's high level. It's good. It's actually fairly easy to learn. But we won't get every bit of performance out of our computer that we might otherwise want. So you might at some point hit yet another limit. Now your problem is not only too complex to just do in a click sort of way. Now you have to go deeper and write a program that does this fast. So we're going to pretend we're still in the interpreter part. Okay, that's this course. So we're using Canopy. We're using Python. Python comes roughly in 2 flavors, version 2 and version 3. About a decade ago, version 3 came out. So you might wonder why we're still sticking with version 2. And it's just because version 3 is not compatible with version 2. And not every package that we might want to use has been ported to Python 3. And so that's why a lot of the world still uses Python 2. It's version 2.7 point something by now. If you get your standard Canopy one, that's the one you'll have. And there's no shame in using this, even if it's 10 years old. It's not 10 years old. It's still updated as version 2. So Python then. OK, so we've done the research. Well, you have done the research, or you know what it is. We've done the research computing part. Python, scripting language, interpreted. It's free. It runs virtually everywhere: Windows, Linux, Unix, Mac, and has a huge amount of stuff in the standard library, but even way more in third-party modules. And so any functionality that you might need, there's probably a package for this. This sets it apart a little bit from R, for which the same is true. A lot of the built-in stuff in R has statistical functionality right in there, which is very good if you're doing statistics. But Python is more general purpose. So the language is more basic. It doesn't have that much functionality in terms of specific research computing. It's good as a language. It's very general. But it has this massive amount of packages. So depending on what you're doing, if you're doing 4-dimensional arrays and analyzing something in that, there's a package for that. If you're doing sort of Excel table kind of lookup, data processing, there's a package for that. So for everything, there's a package. And these are fairly standard, well developed. And so for everything you might want to do, there's probably a package out there. So it's not all that much programming you will have to do. Big building blocks are right there, and that's great. It is, however, slower than C and Fortran or even MATLAB, just because of this interpreted nature and the fact that there's no optimization between different commands. And you should know there's Python 3, but you should not use it for this course. Okay, so these are the 3 things in our title of the course. And then, just to make things complex, apart from Python, there is IPython. And we'll be using it too in a very sort of low-level way. But Python has a prompt. You type a command, it does it, it gives you back what the result is, and you type another command. So that sounds like it's interactive. So why do we need IPython, which stands for Interactive Python, if it's already interactive? And it's in essence all the things that Python interactively doesn't do very well, IPython has been improved upon. So there's this way. Well, let me give you an example. In Python, you can have a data set and you say, plot the data sets. And it creates a plot. But it doesn't show it to you, because you haven't asked it to be shown. You said, make a plot. Somewhere in memory is this plot. So it's interactive, but it's not the interactive thing that you have in mind. There's ways to show it then, right, with yet another command. I think it's show. But there's these small things that make it a little bit annoying to work with in a real interactive way. IPython is different. It has been tweaked and enhanced to make this work. So if you plot that data set, it pops up and you see it, as you might expect. So for a lot of the playing around, IPython is great. It loads a whole bunch of packages by default as well, so you don't have to load every package under the sun. There's a good bit of functionality there. And so that's one of the things that we'll be using. It's just an enhanced version. There's a thing called the IPython notebook that I'll only mention, but it sort of gives you in your browser a MATLAB, Maple, Mathematica kind of environment where you have worksheets and stuff like that. It's nice, but we won't be using that, even though it's nice, because we don't really need all of that. Yeah, a little bit. It's a little bit like the RStudio prompts that you have there. Yeah. So Canopy is really sort of the equivalent of RStudio in this respect. It's a better analogy, I think. So here's what it looks like when you, or this is the website. So and the nice thing about it, and it's not the only one that does this. So there's things like Anaconda and other. Forgot the other one, but this is not the only packaged Python solution. But we chose one, and this one works everywhere, so that's good. So it has. This is kind of what it looks like when you go into the editor. And what's nice about this is that you'll have an editor that will take your Python code. And then here you have an IPython prompt. So you can play around here, type commands, plot things. You'll see them right away. But it's an integrated environment in the sense that if you have this file here, you press the play button, it runs that code. So you can write a script, a set number of commands, and that's what you will have to do if you're doing the assignments, and just run them and see if they work or if they do what they're supposed to do. And you have other functionalities too, but this is what it looks like. Yeah. In the academic license, it has that. So you can indeed go line by line, see what the values of variables are, and this is very useful. This has actually only been added, I think, in the last year or so, but it's a good feature. There are other debuggers for Python. It's not the only debugger out there, but this, yeah, it integrates with that. But you have to get your academic license for that. Free one doesn't. I mean, I guess they they have to have some way of sustaining themselves. They do sell this commercially as well. So if I plotted something, it would just pop up. Here's a figure that's very uninteresting. Okay, so that's the environment we're going to work in mostly. We don't have to, but we'll pretend that we're all doing that. Okay. Clear? So by next lecture, if you don't have this already, get this installed. It'll be fine. So how about Python? So we know there's an IPython prompt. We know there's Python. We're going to do research computing. What's this Python language all about? So we're going to go through a few things. As you guys have programming experience, once you know one programming language, you know them all, except you have to know how to do X, Y, Z in this language. So I'm going to go through this fairly quickly. Ask questions if you want, right? But a lot of this is going to be extremely simple if you're well-versed. It's going to be good to know if you're a beginning programmer. So we'll just go through them and get everybody sort of in a similar level. So first thing, variables. Variables are names to data, or think of them as little boxes where you put a value in. You can get that box back by its name. So I can say x is 2, and then whenever I say x, it'll be 2 until I change what's in x. Same with y equals 2. This is the IPython prompt. So the IPython prompt does, this in is your command, and then out is when something comes out. Nothing comes out from an assignment. It just happens. Okay? If I typed in 2, it would give me 2 back. If I give an expression, it gives me the value of the expression back. If I give a command, like an assignment, that doesn't have a value. It's just something that is done. So that's why nothing gets taken. If I print x plus y, print is the way you print things. I could say x plus y, and it will tell me 5 as well. Print is more for non-interactive things. So if it's in a script, you would have to type print. So it's good to do print. You can add things, you can multiply things, you can divide things, much as you would expect. Note that I don't have to say what type x or y are. It automatically figures out that these are supposed to be integers here. I don't have to predefine them. I don't have to undefine them. Math kind of works as you expect. The numbers, that's in there. Integers, floats, complex numbers, they're all built in. Strings, so bits of text are in there. Lists are in there with these square brackets. And if you have a list, you can ask for an element from that list by using square brackets as the indicator to get a particular index. This is strange. Oh. So I can get it, but I can also use it to allocate. So I put this list that has 3 elements, and element 1 is 2 to 6. And then when I print the list again, it gives me 6 in element 1. Element 1, yeah. So if you're coming from a C background, you understand why. If you're coming from a Fortran or maybe even R, element 1 is the second element. Python SC starts counting at 0. 0, 1, 2. Think of what's between square brackets as the offset from the beginning. Then this is offset by 0 from the beginning because it's already the beginning, offset by 1, offset by 2. So element 1 is the second element. Something to get used to if you're not used to it, but it is consistent. And that is all. It's like driving on the left rather than the right. It's not bad, it's just different. You can have tuples, which are kind of like lists. You can have dictionaries. Dictionaries are interesting. I find them interesting. They don't have that much use in scientific computing typically, except in those cases where they have. They associate with one key value, with one key, one value. So whenever I say S, it'll say, oh, an I is associated with that. P, LS. So it's kind of like a translation of one thing to another. And they can have anything. They don't have to have strings. They can have numbers. Pretty much anything can go in as a key. And they're basically a fast way of looking things up. You make a list. You label them with whatever key you want. You say, I want the value of that key. It starts looking up. And it does it in a very clever way. Clever meaning it's fast. So this is very useful, and you should never have to program a search yourself, not in a linear list for sure. Okay. So they're distinguished by the syntax. The lists are square. The tuples are just parentheses, and the dictionaries are curly because they are more fancy, so they have curly. Tuples, by the way, you can't change anything in a tuple; it's fixed. So that's the difference between a tuple and a list. So a list is very useful if you want to do something that looks like an array, but it is allowed to have different kind of elements in there, I think. So, yeah. So, but it's not a real array in the sense that you have a bunch of elements that are kind of the same. Their values are just different. So if I wanted an array of integers, I can make a list, but now each of these things, each of the parts of the lists would have information about its type stored there as well. And each time when I use it, Python would have to see what type is this and what can I do with this. There's a lot of checking in a list. Each time I just access something. In a real array, the idea is that I have a certain type, say, in this case, it's floating points, and I just have 3 of them, or 100 of them, or 10,000 of them. When I access them, I don't want to check what type they are. I already know they're all the same. Okay? So just treat them as one big block. So Python doesn't have that as a built-in, and that's what I mean with a real array. It's n times the same thing. But those arrays have been put into a standard, well, almost standard package called NumPy, numerical pi. And if you're using IPython, this gets loaded automatically. And it's sort of the backbone of many scientific computing package. SciPy is a whole bunch of higher level ones that builds onto NumPy. NumPy just gives you essentially n-dimensional arrays. You have an array, it could be 2-dimensional. You can manipulate them. You can multiply them. Here I have an array. Well, x was something. I can multiply them with a scalar. I can multiply them element-wise. We'll have a whole lecture on how to use NumPy and the features it has. But it's the thing that can make your stuff tolerably fast. So as I said, pure Python is extremely slow, but it's versatile and very good to do general stuff with. Things like NumPy are more restrictive because all of these things have to be the same type, right? But by using that, it can be faster. Wanted to mention these guys one more time just to know what they are. So the tuples are like lists, but you can't change them. And the reason you have to know them and why they even exist is that if you can't change them, there are certain things that can be done faster again. So a lot of functions might return a tuple and say, this is it. Can't change this. The dictionaries, which are these key value pairs and good for lookup. Keys can be anything, a string, an integer, a floating point. And they don't even, this is the flexibility of Python. One dictionary can have a key that is an integer and at the same time, another key that is a string. But that flexibility costs you, right? So that's why you don't use those if you don't have to. It's very handy, but it's not very common. Like in scientific computing, you have data. It's of a certain type. Typically, you collected it. You're not going to compare, I don't know, the quality of wool with the number of people in all of the buildings. That's not one data set, right? It doesn't, and then the names of the sheep. No, right? So scientific computing tends to be more uniform, and that's why you don't use them much. But it's good to know that they're there when you need them. Objects, just want to mention, they are there. Python can do object-oriented programming. All the good stuff is in there if you like that sort of stuff. We're not going to cover it because it just makes things more complex than they need to be for a 1-month course. Data frames, things like, it's the kind of stuff that makes things look like R a little bit, or Excel sheets or tables, where you want to select certain columns. It's sort of a column-based thing. Things that can be labeled. Good stuff, but again, probably a little bit too specific for what we're doing, but this is in the package called Pandas. Good to know that that's out there if you're doing a sort of table-based stuff. Okay, so suppose we have a list. I'm going to go back. And I wanted to do something with the list. Well, I have to go over each element and say print it. How do I do that? That's a loop. Every decent programming language has a loop. Before there were decent programming language, there was a go-to statement. And people don't like goto statements because it makes things messy. So a loop. How do I loop over all the elements of a list? I use for. For element in Z. Z is a list. Element gets assigned the value of each of the elements of that list, one at a time, and one at a time. And for each of them, it does print elements. This shows you one thing that is interesting of the Python language. It's that indentation not only is important, it is vital. It matters. If you do indentation wrong, Python won't work. So for is not indented, so this space is just static. So think of it this way. But then the next line is indented. That means that that is the line that this for statement executes again and again and again. I wanted to have two statements that were both executed together for each element. I can have an extra line that is indented by the same amount. That's how I show to Python what my blocks are, so as one single block. In R you would and C with curly brackets. Fortran is full of begin and end, or end statements. Python does it with white space. White space being tabs, spaces, indentation, enters. Okay, I can create lists on the fly as well. So if I want a range of numbers, if I want to do counting, I create just all the numbers from 0 to 9 with a call to range 10. There's two range functions, range and xrange. They do the same thing functionally. They do it differently in the background. But if I want to count, I do this. Note the funny thing is that I mentioned 10, and it only goes up to 9. So it creates 10 numbers, but it starts counting at 0. Python starts counting at 0. So xrange 10s give me 0 to 9. Use x if you don't need the whole list at once, because what xrange actually does is creates just the first one, it prints it, and the next time you try to get another one, it generates it. So there's only one number in memory at any given spot. This doesn't matter here because it's just 10 of them. But if you had to go through 10 million numbers, you don't want to create all of the 10 million numbers. You just want to create one and the next and the next and the next. That's why there is this special number, special xrange versus range. Okay. So loop functions. Decent programming languages have functions. You define a function in Python with def space, and you give it a name, and then between parentheses, you give it the names of the arguments. It's not a typed language. You don't have to give types, but you can return something from the function. So you can return x times x, and it doesn't really matter what x is. I don't have to say if it's an integer, a double, or a string, for that matter. So I can print the square of 4, and it gives me 16. I can print the square of 7.3, which is a floating point, and it'll give me the answer. And I can try and print the square of no, string no. What do you think that would do? What would it mean, multiply no by itself? It's a no-no, right? It doesn't work. So what happens here is that Python doesn't check whether this is valid until you try to do it. It'll complain. If you try this out, it'll say, I can multiply a string by a string, but it will only do it when it started executed this function. This is typical of an interpreted language. It stored this definition, but it's just a prescription. Like it doesn't do it yet. It just says, okay, whenever you're ready to call the function, I'll execute these commands. Once I say no, I put it in. It tries to multiply no with no, and only at that point does it say, hey, that doesn't make any sense. So you can write things very generically, but it also means that when things aren't working or you use them in the wrong way, your errors pop up kind of on a low level. So the flexibility sort of sometimes it's a downside. Control flow, there's an if statement, and that should not surprise you. So if n is even, you print even, else. Same thing. You don't forget those colons. Colons are very important. They say a block is to follow that is indented. Percentage sign, by the way, is the modulus operator. It sort of inherited that from C, I guess. So if there's a zero remainder, it's even. If there's no zero remainder, it's off. So can call the function simply by their name and then given the arguments. So these are functions that do not return a value, and that is perfectly okay. In other programming languages, those might be called something else, routines, procedures, I don't know what. Python has no issue with it not returning it. So those are a few of the building blocks. And then we're going to make a point of modular programming. So I just want to mention that you can write modules. So there's a whole bunch of modules out there already. And when you install Canopy, they'll be there. But they won't be ready to use right away. And that's really because some of these packages might have functions that have the same name. You can't load them both because they would have the same name, and you would have no way of distinguishing which one is which. So the way you would access a package is by the import command. So if you say import and then the name of a package, you could say, for instance, import NumPy, it will import all these definitions of whatever is in that package. Yes. Yeah, no, that's true. I'm being a little. I wanted to make the connection between these two, but I think I. Yes, that's true. So if it's a standard package that's installed, you just say import name of the package. But you can write your own package. And the nice thing about Python is any Python file script can become a package. So if I have a file that is called mymod.py, and by the way, .py is a typical extension you give to Python scripts, and it contains the definition of a function, then that is automatically now a module that I can get by doing import mymod. It should be in the same directory for it to find. You can imagine that. There's other default paths where stuff gets installed, but those are details. But this is, I've now created a module. It's that easy. It's rarely this easy in any language. A file with a bunch of definitions is a module. You import it. But one of the funny things that does happen now, though, is that yes, it imported it, but to call my function, I have to prepend it by the name, mymod.myfunction. So this is one way in which it makes sure that I can't have name clashes. I could have two modules that both define myfunc, and that would be fine. I can import them both. It's just that when I'm using them, I have to say mymod.myfunc. Now, there's ways to make myfunc not have to have this prefix, but by default, this is what happens when you just import the whole thing. Now, when you're writing functions, so I'm giving you a lot of things ahead of time, but this is really more of an overview anyway. Where are we? Sure. So, yes, but only within the file. So I don't have to indent this whole thing or anything like that. But yeah, so the indentation is just as important on a per file basis. But what makes it hard, or the thing that sort of bites you with indentation, is that it's copy paste. You can't easily copy a piece of Python code into another part of the Python code if they're not at the same indentation level. You're re-indenting for this to work. That's kind of annoying. But you shouldn't be doing cut and paste. You write a function. So yeah, that's the indentation has to be correct given the context, but it's per file. Mm-hmm. Well, no, because your editor doesn't know where your blocks are supposed to end. So the auto indent in Python is very hard because by white space you say where things are, which isn't true for most other languages. Like anything that has curly braces, they have to match. Auto indent will work. End statements in Fortran, same thing. But auto indent in Python is very. It doesn't know where stuff is supposed to end. So a few points that I've used in this slide too that I just want to mention is comments. You start with a pound sign or a number sign. Anything behind it is a comment. So you can have a line and then have a pound sign, and the rest is a comment. They get ignored. Comments are important. Comment your files. Say what you intend to do. Say what you haven't done yet, perhaps. In this case, I'm just saying what the name is of the file. Even that can be useful at times. Commenting is a good thing. It's hard to comment too much. It's not impossible, but you can do it deliberately. It's easy to do deliberately, but just comment something that you think needs to be commenting. Just write a note. Anything you think will help you understand your code in, say, a month should be a comment. And so that's good. There's this other funny thing here that has triple quotes. So quotes start a string, double quotes as well. Doesn't matter which one you use as long as they match. Triple quotes do this thing that I'll do a couple of things. But what I do here is essentially make this into the help function of this command. So by having this first line of the function be this triple quoted string, when I type help in the name of the function, it gives me that string. So it gives me the definition of it and the string. So it's very handy and easy to document your functions. And you should. You write a function, write a 1 or 2 line description of what it's supposed to do. And not only is it good because it's in your code, when it's imported, you can see what it is. So that way, for any function that is in a standard package, where you type help, a useful message comes up about what this thing is and what it does. Okay. Continuing on with sort of an overview. You can do indexing, so you can get element 2, as we saw before, so 0, 1, 2. That's the thing that's called 3. I can get the whole array with colon, but I'm actually getting a, well, that's good. So that's everything. But I can do slicing way more specifically. So I can say go from element 1 to 3 and get me that subsection. The colon is sort of a range operation of the indices. It does it in a funny way, though. Not only does it at 0, it also gives you everything except for the last number. So it's all but 3. So start at 1, so that's 2. That's 0, 1. Start at 1 and give me everything until you hit 3 and don't give me 3. So 0, 1, 2, 3 is 4. So don't get 4. Everything but this last one. So it starts to 1 element after end. It's a weird thing weird way of doing it. I don't really like it, but it's what Python does. There's arguments why this is a good thing, but it's what it does. So when you're doing a slice of an array, first element and last element plus 1 is what you're giving. Okay. You can do strides. That's kind of neat. So you can go count in 2s, right? So 2, 4, 6, get the element 1, 3, and 5. Yeah, very nice. So that's a stride. That's extra colon. Right? Good for picking things out. You can plot. If you're doing this in IPython, that's great. It pops up right away. So if I make an array, X is an array, 1 to 7. So I made a list. An array is actually a way to call a NumPy function and make it into a NumPy list. NumPy is loaded by default in IPython. And I said that we'll go through all the details, but I have a list now. And now that I have this array as a NumPy array, I can multiply it element y, so x by x. So y is x by x. This takes every element from the list and multiplies it with itself. That's nice and concise. And that's NumPy for you at work. So as I said, details of that we'll see later. And then I can plot x versus y, and I can give some arguments saying what I want it to look like. They are cryptic, but convenient. It's red. O means it's dots, and dash means I have a line between the dots. And there we go. We have a line. It's not a great plot, so we'll look at how to make this plot great towards the end of this course. But it's a plot. And so this is part of what's called matplotlib. It's a plotting system that's sort of modeled a little bit to MATLAB. And it's very good when it works, but it gets very tricky to get it to do exactly what you want. So we'll focus a little bit on that, the visualization lecture. But for quick plotting, good stuff. I can plot things on top of one another. So if I keep plotting, It just keeps adding lines to the same plot. If I don't want that, I have to clear the plot. But so I can have a green plot here and a blue plot here, sine and sine 2x. And linspace is another NumPy routine that we'll see. Gives you basically a grid between, in this case, 0 and 2 pi, is 75 points total. Pi and E are also in matplotlib. They're not in Python. Files, you can do files in Python. We'll have a whole lecture on files as well. I want you to know that this is all possible. You can save a NumPy array, you can load it. And there's built-in file objects which do sort of the low-level stuff. I open a file, I write something to it, I close it. And that's fine, but there's things that you might also want to do, like create a directory, see if a file exists, check the path. So those are in yet other packages like OS path, sutil, sageutil. And then there's things that do that allow you to write stuff without having to know exactly how it's laid out. So if I'm writing text, that's easy. I just open a file, I write it. If I'm writing a dictionary, what do? Do I write all the keys and then all the values? And I have to figure out a way to format, come up with a format. No, there's a way to do that. The most general way to write anything Python-y to a file is to pickle it. You have an object, you pickle it. It means that Python figures out a way to write this out such that I can read it again. That is useful, but it's not fast. It's slow, and it's dependent on Python, and nothing else can read it but Python. It's good for saving Python things for Python to use later. There's things to get the whole bunch of pickles together. It's called a shelf. But there's things that you might want to have things a bit more portable. So you can write out in JSON if you know what that is. You can zip things, you can tar things, you can write things out as comma-separated values. NumPy has a couple of ways of writing things out. You can use portable formats like netcdf or HDF5, if you know what those are, and we'll tell you a little bit if you don't. So more portable things. They can be read by things that aren't Python. So we'll go over this in a whole lecture because, and this might be something you don't know, the disk I/O is the slowest part of any computer. Even your Wi-Fi is faster than your disk. Okay. We at supercomputer centers try to get around that by having a lot of disks at the same time. You don't have that luxury typically, right? So the disk is slow. And so what you do with the disk is important. That part you don't want to worry about it, just saving or reading things. Why am I worrying about it? But if it's the slowest part, if you spend 2 hours waiting for your data to be read, you spend a minute computing it and then another 2 hours writing it out, now your I/O matters. And probably it matters because you're doing things in a way that isn't great for your particular file system. So knowing a little bit about how to do that well can save you time. So that's why we do that. It's not the most exciting part, but sometimes it's the bottleneck, and you have to know this. So lots of ways of doing that, lots of packages that help you with that. And that is a downside of being very modular. You sometimes just have to know a package exists, and that's why those things are in there. Just look for those modules, and you'll see what they can do. And then one of the last things I want to mention, since we're going to be working in IPython and doing some sort of hands-on stuff and plotting things, what if I want all of that to work in my script? So IPython loads things like NumPy, SciPy, Matplotlib, those nice packages especially for numerical stuff. And if I make a script, so a pure Python script, and I try to run that, it won't work because it doesn't have these things loaded. So the easiest way to get this, and it's not the best way, and people will scold me for doing this, for telling you this, but the easiest way to make stuff that works in IPython work in Python is to say from Pylab import everything. Pylab is sort of this thing that makes IPython work, and this loads all of these things in your Python script. It's not great because you can get things like name collisions, and it's bad practice to import everything from a whole bunch of stuff. But if you need to have something that you carefully made work in IPython work, this is how you would do it. And then there's one more thing. You're trying to do this with graphics. Remember, I said plots don't pop up in IPython, or in Python. They do in IPython. They would if you paused a little bit. So there's something in the background, some sort of a thread that's waiting, and it's just stuck because if you pause for a second, it gets a chance to run, and this is the thread that does the displaying. So pause.1 gives a 100 milliseconds pause, and it's often enough for this to pop up. Weird, but thought I'd mention. So that's today. I want to make it too long. I want to give you an overview of the language. I don't expect you to understand every detail, but if you knew what loops do, if you knew what variables are, if you knew what packages are, you kind of have an idea of how they work in Python. As we go through the course, we'll have more sort of concrete topics. Next topic will be numerics. That essentially involves anything that can go wrong if you're doing any numerical analysis.